So in the last video, we went through an example of how to graph a rational function. In this video, you're going to go through some practice problems, work through them on your own, and then we'll go through the answers. So before we get started, it would be a good idea to have some graph paper and a graphing calculator before moving forward. So here's our first problem. It says graph f of x equals x cubed minus 9x divided by 3x squared minus 6x minus 9. So at this point, I would pause the video, copy down the problem, and work through finding each of the key features, putting it on a graph and sketching the general shape. Okay, so hopefully you've worked through this problem. And the first thing we always need to do is to make sure we factor. So we can see that both the numerator and the denominator are not factored for this problem. So we're going to go ahead and do that. So for the numerator, we see that we have an x cubed and an x in both of our terms. So that means we can take out a GCF. So we can take out a GCF of x, and then when we do that, we're left with x squared minus 9. Well, you should notice that x squared minus 9 can actually be factored down even further because it's a difference of two squares. So it can actually be factored to x plus 3 and x minus 3. And then if we look at the denominator, 3x squared minus 6x minus 9 also has a GCF. You can see that they all have a 3 in common. So I can take out a 3. And when I do that, I'm left with x squared minus 2x minus 3. So now I can continue to factor using the AM method. So I still bring along that 3. And then I can factor this to what adds to negative 2 and multiplies to negative 3. So those two factors are going to be negative 3 and 1. So I have x minus 3 and x plus 1. So I've got a lot going on here. So I want to break it down to each of these key features here. So the first thing I'm going to look at is, does anything cancel? And it does. So I have my x minus 3's are going to cancel, which means I know I'm going to have a whole at x equals 3. Remember, it's always going to be an ordered pair, so I got to plug it back in to find my y. And it always helps to write down that simplified rational. So after I cancel my x minus 3's, I'm left with x plus 3 over 3x plus 1. So now I can go ahead and plug in 3. So when I plug in 3, I get 3 times 3 plus 3 divided by 3 plus 1. So I can say I'm going to have 3 times 6, which is going to give me 18. And then I'm going to have 3 times 4, which is going to give me 12. And 18/12 can be reduced even further to 3/2. Because I can take a 6 out of both. All right, so now we're going to look at the denominator to find our vertical asymptote. So our vertical asymptote comes from our denominator, and when we set this equal to 0, the 3, when we divide that, still gives us 0, and then we subtract over the 1, so our vertical asymptote is going to be at x equals negative 1. And our horizontal asymptote, remember, it's always better to kind of go back to the original function to look. So if I look at my highest degrees, I have a 3 and a 2. So that means I have large over small. So I have listener. So that means I have no horizontal asymptote for this function. And then the last piece we're going to look at is our 0 or x-intercept. And remember, that is taking our numerator and setting those pieces equal to 0. So here I have x is equal to 0 and x plus 3 is equal to 0. So when I solve those, I get x equals 0 and x equals -3 are my zeros. So at 0, 0 and -3, 0, that's where it's going to cross on the x-axis. So let's go ahead and plot those key features over here. So our vertical asymptote is going to be at -1. So we want our dotted line. And then our horizontal asymptote, we don't have, so we don't plot anything. We have a hole at 3, 3.5, so at 3, 1.5. So we're over at 3 and then up to about 1.5 there. And our zeros, or x-intercepts, we said we're going to be at 0, 0 and -3, 0. So we can already see that we're going to have 2 integral points on both sides. But let's take a look at the graph using our graphing calculator to get that general shape and see if we can find another point or two to make it a more accurate. So when I put it in my calculator, this is what I should see when I look at my graph and when I look at my table. So I can see my general shape from the graph portion, and from the table, remember when I see an error, like I do at -1 and at 3, that represents where our domain is essentially. So -1 is where that vertical asymptote is, and 3 is where our hole is. So remember, if there's no part of the graph there's no outputs. So that's why we have an error. So we can graph some of these points. We already graphed -3, 0, and we graphed 0, 0. If we wanted to, we could take a look at some of these other points to plot. None of them work out super nicely. So we do already have 1 point on each side, so that would satisfy what we're looking to do here to graph. So we're just going to look at the general shape here. And our general shape, we're going to sketch. It goes through 0, 0. It goes towards our hole, stops at the hole, and then continues on. Make sure we have our arrows because it does go on forever. And then we come around here and we're going towards our asymptote, but remember, never touches or crosses that. And then over here at -3, 0, we're going to go up towards our asymptote and then away this way. So this one looks a little different than ones we've seen before, but it is still a rational function and it's got our key features. This one has a hole, x-intercepts, and then it also has that vertical asymptote. Once again, we've got another practice problem. We've got f of x equals 4 divided by x squared minus 6x. So go ahead, copy this down into your notes, give it a try, and then come back and check through your answers. So hopefully we've worked through this now. So always, always, always our first step is to factor our numerator and our denominator. Our numerator is already as low as it can be at 4. So that's going to stay. And our denominator, we don't have a difference of 2 squares even though we only have 2 terms. So we're just going to look for a greatest common factor. And both of these terms we can take out an x. And then we're left with x minus 6. So that's as low as we can go. So first thing we always look for is, does anything cancel? And nothing in this function cancels. So that means we have no holes. So next we're going to look for any vertical asymptotes. So vertical asymptotes, remember, we look at our denominator and we set those equal to 0. So we have an asymptote at x equals 0 and at x equals 6. We'll have 2 on this graph. Then looking for horizontal asymptotes, if we look at our original function here, we have no degree and we have a degree of 2. So we have small over large, which means we have slow, and we have a 0 for our y asymptote. So y equals 0. Then we look at our numerator to find if we have any x-intercepts, and we don't have any x's, so we don't have any x-intercepts. So we have no holes, and we have no x-intercepts. So let's plot what we do have. We have vertical and horizontal asymptotes. So our vertical asymptote is going to be at 0. And we have one at 6. Then we have a horizontal asymptote at y equals 0. Now, we want to go to our graphing calculator, graph it, look at our table, find some points on here to plot our general shape. All right, so I went ahead and graphed this. Hopefully you graphed it as well on your graphing calculator. So looking at our graph, this one looks a lot different than the ones that we've done before. We've got 3 different pieces to this rational. So we look at our table here, we see that we have one piece that's going to be over here on this side of our vertical asymptote. We have our piece in the middle, and then we have our piece over here that is on the right side. So we want to find at least one point in each of these sections to graph, so then we can sketch our general shape. So none of these points work out super nicely, so we want to pick one that's going to be the easiest, and I would say that would be at -2 1/4. And then if we look through there, we have 4 -1/2, and then 8 1/4. So no super wonderful points, but these ones will do, and it'll give us at least a starting point for our sketch. So if I put these points on my graph, I have -2 1/4, I have 4 -1/2, and I have 8 1/4. So my graph goes through each of these points. Now I know on this picture here, it looks like the graph stops right here and right here. It doesn't. If you were to zoom in on your calculator, you would see that the line is there. It's just getting really close to that vertical asymptote, that axis there. So you can't see it all, but if you were to zoom in, you would see that this graph does in fact continue. So that's what we want to do with our graphs. We should know that these rationals are going to continue on towards those asymptotes, even though it may not look like it there. So on our left side, we're going through this point and we're going up towards our vertical asymptote and then towards our horizontal. This middle piece is kind of that upside down U shape, going towards both of our vertical asymptotes. And then on the right side, we're going towards our vertical and our horizontal asymptotes. And then that would be our graph for this rational function. All right, we've got one more example for you guys to try out here before moving on to your homework. This one is f of x equals x squared plus x divided by x squared minus 1. So write this down, work it out on your own, and then we'll go through the answers together. All right, so we always start with our factoring. So we want to factor the numerator, and when we factor our numerator, we can see that we're just going to take out a GCF. So our greatest common factor is x, and when we take out an x, we're left with x plus 1. And in our denominator, we have 2 terms and we have a difference of 2 squares. So we're going to have x plus 1 and x minus 1. As we've done before, first thing we look for, does anything cancel? And yes, it does. Our x plus 1s are going to cancel, which means we're going to have a whole at -1. So let's go ahead and rewrite our simplified rational. And our simplified rational is going to be x over x minus 1. So now we want to find our y coordinate, and to find our y coordinate, we're going to put in our input of -1. And when we do that, we have -1 over -1 minus 1. So this is going to give us negative 1 over negative 2, which is going to simplify down to 1/2. So our whole is going to be at negative 1/1/2. Then we want to look for our vertical asymptote. And remember, vertical asymptote, we're looking for that denominator. So when is that going to be 0? Because we know there's going to be no points there because it's not in our domain. So our vertical asymptote is going to be at x equals 1. And then looking for if we have any horizontal asymptotes. We want to go back and look at our original function. And if we look at our original function, we have a degree of 2 and a degree of 2. So we have the same on the top and the same on the bottom. So that tells us Southside Chicago, we're going to look at our coefficients. And there's no numbers out in front, so it's just our ones. So 1 over 1 is going to be what our horizontal asymptote is, which is just going to be y equals 1. All right, and then last but not least, looking for those 0 or x-intercepts, we look at our numerator, and we just have an x. So if we set that equal to 0, our x-intercept, or a 0, is going to be at x equals 0, or 0, 0. So let's go ahead and plot these on our axis. So we have a 0, or an x-intercept, at 0. We have a horizontal asymptote at y equals 1. Then we have a vertical asymptote at x equals 1. So we're going through x and y at 1. And then we've got it all. We've got a whole at negative 1/1/2. So right about there. All right, so now we're going to go ahead and graph. So go ahead and graph, look at your graphing calculator. And I'm going to go ahead and pull up what the graph should look like. All right, so looking at our graph, we can see our general shape here. And we can see at negative 1, that's where we have our vertical asymptote. We have no outputs. And same thing at 1, because that's where our whole is. So remember, removable discontinuity, there's no points there. So let's pull up some of our points that we can plot. We know we need some points up here in quadrant 1 and down here towards quadrant 2 and 3. So if we're looking for some good points here, we can see that we have 0, 0 is going to be a nice point, which we have because of our x-intercept. And then we also have 2, 2. That one works out nicely. So we want to have those plotted because remember, at least one, if not more, you can plot as many as you'd like here so that we may have a more accurate graph. So I'm going to have 0, 0 and 2, 2. So I'm at 2, 2 over here. So I know my graph's going to pass through those points. So I'm going to give myself a nice sketch. So I know it goes through 0, 0 towards my hole. It stops there and then continues on the other side towards my horizontal asymptote. And then it comes down towards my vertical asymptote. And then this point up here is coming towards my horizontal asymptote and my vertical. Just be careful when you're sketching these graphs that you don't cross over or touch those asymptotes, because remember, those are your boundaries. You got to stay inside of those. So that's graphing rational functions. Make sure that we go do our worksheet so we get even more practice at these, and you ask if you have any questions.